He did his PhD in 2011 from Florida State University, and then he did a couple of postdocs at Texas A&M Commerce and the Indiana University, and then he joined as an assistant professor in the Manhattan College, USA.
Yeah.
And we all know that he has been really very actively working on the hello.
Yes, yes.
So he has been working on the, theoretical front, various problems associated with neutron stars, and the important point is the physics of the neutron stars with the connect to the object of the. So I would like to welcome Professor Farrukh to deliver his presentation on the neutron-rich matter and the.
Thank you so much for a nice introduction, and I'm very happy to be here. And thank you so much for giving me this opportunity to talk about our recent research. And I've been at IUCA. I was invited 14 years ago, and it was a pleasure to be there for 2 months. So I'm now very excited to be back, although remotely. And I would like to can I start now the talk, or?
Yeah, you can start.
Go ahead.
So much. So I just wanted to give a brief overview of a general overview of neutron star formation and some historical facts, given the diverse evidence that we have here, and then I'll go on to discussing the nuclear physics of neutron stars and some uncertainties that are related to the equation of state of neutron-rich matter, and eventually I'll discuss about recent binary neutron star mergers and gravitational waves that are coming from these neutron star mergers. How do they constrain our knowledge of the equation of state of dense matter? So first, let me take you on a brief journey about neutron star formation, following the footsteps of radii on a story of our universe after the. So this will be about 5 minutes, though. I'm not going to talk all the things. So it's about 13.8 billion years ago, as we know that the universe is formed in the Big Bang explosion. And of course, going past the inflation stage, in the very first 3 minutes, we've got all these elements, light elements of hydrogen and helium were created, and some traces of light elements were formed. And for many million years, about 500,000 years, there was a stage of dark ages that no further elements were formed, and the first stars appears only about 1 billion years later due to gravitational collapses of these gases of hydrogen and helium. So these stars evolve, and as clouds of these gases collapse, the gravitational energy turns into thermal energy, and at a very high temperature, the core of the stars initiates thermonuclear fusion. The temperature has to be really high, and the pressure has to be sufficient for the thermonuclear fusion reactions to occur. Only for very massive stars of about 8 to mass, this thermonuclear fusion continues from lithium all the way down to the formation of the iron core. And no other are ever produced, so our periodic table is filled element of 26. Now, this stage of formation, as you can see, goes from triple alpha, from hydrogen and helium burning and triple alpha reactions, and then oxygen, neon, carbon, magnesium burning. So you have CNO cycle here and silicon burning, and then all the way to the iron. Now, as iron core gets bigger, and especially when it gets about 1.
Hello? We lost the connection, I think.
99% of the gravitational binding energy of this supernova is radiated in neutrons, and of it tidal that either a neutron star or a black hole. So every carbon in our cells, as you can see, oxygen that we breathe, the calcium in our bones, iron in our blood, are the results of this supernova. In fact, we are this stardust. And I would be talking about this particular compact object known as a neutron star. And for black holes, there are many topics that general relativists with. So here is a bit fun facts, historical facts, and the main actors of this stage. So the first actor or the first great scientist that, as you know, is history is this famous Subrahmanyan Chandrasekhar on his trip from India to England, and he was just 19 years old. He worked out the whole statistical physics of a degenerate Fermi gas, and not only he worked them out, but he also applied white dwarfs. And in particular, he wrote that for a star of small mass, the white dwarf stage would be the initial step towards the complete. So that would be the death of the regular stars. But he said that if the star is very large, they cannot pass through this white dwarf stage, and then one is left for speculating on other possibilities. This limit is known as the Chandrasekhar limit, and by many scientists of the time, Eddington, but eventually, of course, as we know, he went on to win Nobel Prize for his discovery. A year later, almost at the same time, actually, independently from Chandrasekhar, Lev Landau, he was also about 22 years of age, obtained a very similar result, and then he went on actually speculating what would happen further. And he said, in particular, that density of matter becomes so great that atomic nuclei come in such a case and form one gigantic nucleus. Landau was in Copenhagen at the time, and as you may know, Newton was not discovered yet. So it was only discovered a year later by James Chadwick, and therefore the word neutron stars was. And 2 years later, of course, Bade and Sweetie went on to discussing that supernova must represent transitions from ordinary stars to neutron stars. And the first calculations of neutron stars using general relativity were actually computed by Oppenheimer and Volkov. And in particular, they found that the maximum mass of a neutron star must be about 0.7 solar mass. And they commented that, and as we know today, it's not very far from true, and how wrong they were. And that's the part that I will be talking. The first neutron star was actually discovered by Jocelyn Bell at the age of 24. This story is interesting that I would like to share. For those who are not familiar, it was the August of 6 of 1967 when she was working under Anthony Hewish, and she discovered a very variable signal in radio frequencies that had extreme regularity in period. As you can see, the period is very exact. And she, of course, had a note that this could be from another civilization, maybe, but of course, there was no explanation yet. So she wrote on the note as LGM. And they were thinking of the possibility of what it could be. And of course, after some discussions, they figured out this would be the so-called star that was theoretically already predicted. The paper was published in Nature by Anthony Hewish, and they went on to the Nobel Prize. The Nobel Committee somehow thought to graduate students, so they did not share the award with Jocelyn Bell. The Nobel Committee was roundly condemned by many astronomers, including the famous late Fred Hoyle, who is a very close link to actually IUCAA through Professor Jan Narlikar. And breakthrough prize for which she donated all of it to underrepresented students and women in science. So what's a neutron star? Let me give a little biography. Known neutron stars today, as you know, is discovered in the first supernova that we know is discovered and today is left a neutron star known as the Crab pulsar, was discovered in 1054, and they were documented in multiple Chinese and Japanese documents. And this event was even recorded in Anasazi residence of New Mexico. And the leftover Crab Nebula at the center, it has a Crab pulsar, which is at the distance of about 6,500 light years. Their temperature is very large usually, but however, because they are much smaller than the Fermi energy, we call them cold neutron stars. The density of neutron stars are extremely large of nuclear densities, and their pressure is 30 orders of magnitude larger than atmospheric pressure, so they're extremely strong, and they possess strong magnetic. And they're of the size of 10 kilometers. That's what the nature of my talk is, and they spin really fast. And for example, neutron stars are and compact that if you let one of them compare them with the map of Manhattan that I'm currently here, something like this. And the density is so much large that entire population of the Earth could be fit on a few sugar cubes. Surface gravity is extremely strong. In particular, the famous jump by Felix Baumgartner that took about 20 minutes for him to jump of the height of 39 feet, about half millisecond. So there are extreme physics involved, and I will be talking about the nuclear physics part of it. Here, let me talk a little bit about the anatomy of a neutron star. They can be subdivided depending on their physics involved, several parts. A very thin layer, upper layer of 10 centimeters is atmosphere, shape of which is created by the thermal radiation. And a few first 100 meters are known as the outer crust or the envelope crust, or you can study together. There's a very strong gradient. And in the outer crust, you have got arrange themselves in a Coulomb crystal. The density increases and you go towards deeper sides, and you inner crust where the crystal now becomes of nuclei that are much neutron-rich. And when these neutron-rich nuclei come closer, there is a phenomenon known as Coulomb frustration occurs between various geometries. And then at the very end of the crust, the density becomes uniform. That the core can be divided into the outer core and the outer core is thought of being. So some fundamental questions and grand challenges can be answered by neutron stars. In particular, it's 4 excellent books and guidance that were recently, especially in the United States. There are some questions of the centuries that says that how does subatomic matter organize itself and what phenomena can emerge. We understand the fundamental interactions that are basic to the structure of matter, and where do the chemical elements come from, and what's the nature of dense matter. And how this matter, most of these are impossible to answer in terrestrial laboratories, and the natural laboratories starts because in terrestrial laboratories, if you bring a piece of star matter, it will expand and explode because they are generally unbound. However, neutron stars are strongly supported by gravity. Now, here is an image of a nucleus on the left side, and then you've got a neutron star. There is a northerly heavy nucleus has about 100 nucleons, whereas neutron stars has about 57 orders of magnitude larger in nucleon numbers. However, their densities are very similar. So on the one side, you have got about a nuclear saturation density, and there you have got an average twice nuclear saturation density. One is supported by the surface tension, the other is supported by gravity. Size-wise, they are 18. Now, they're vastly different in mass, but yet are governed by the same physics of strong interaction. And that's the physics that tells us that the maximum mass of a neutron star is not that 0.7 solar mass that was originally predicted by Oppenheimer and Volkov. So in this picture, in this graph, I plot density of nucleon densities as a function of radial distance from the center of the nuclei on the left side. And the same I do for a neutron star, the density of neutron star matter as a function of density. I plotted two particular equations of state as known state. By stiff and soft, we mean how the pressure behaves as a function of density. And for soft equation of states, it's very easy to squeeze them. That's why you get smaller nuclei, more compact nuclei. Whereas for stiff equation of state, I have larger radii. The same goes for the neutron stars. As you can see, the behavior is very similar. On the final nuclear side, you have got only two participants, neutrons and protons, whereas neutron stars can be much more complex. Neutrons, protons, electrons, and muons would be at least there. However, what I would like to concentrate the density distribution inside the nuclei and neutron stars are similar for both equation of states, and also the density range is very similar. We've got about nuclear saturation density is about 5 or 3 times nuclear. Depends on the mass of the star, obviously. So the sole ingredient that's required in building neutron stars and finite nuclei is the equation of state of neutron-rich matter. Now, how do you build a neutron star? It's basically static equilibrium equations that you have to solve. Relativistic hydrostatic, and for which gradient that has to be a large overcome the force of gravity. This basically of mass contact. You would find that the mass of a neutron star would be strongly depending on the nuclear equation of state or the nuclear forces. Particularly, as we know, general relativistic extensions are very important. That, for example, the speed of sound in neutron stars are about half of the speed of light. And as we from 0.7 solar mass of a maximum mass to 2.5 solar mass is taken by the nuclear physics. So it's the nuclear physics that dictates what the mass of the neutron star should be. There are enormous uncertainties, of course. Radii predictions, that's the main part of my talk. So if I plot the masses of all planets in solar system versus their radii, I get in logarithmic scale something that tells me about the material properties of these planets. There is no good correlation because it's logarithmic slope. You may see it seems linear, but there is no quite good correlation as you see. But however, if you do so the same for the neutron star, there is actually one unique correlation known as mass that's solely dictated by the equation of state. Once the equation of state is known, for exactly determine one single radius. But however, we do not know which equation of state is correct one. High density. Therefore, tons of nuclear models that are extremely accurate in their predictions of properties of finite nuclei, yet they are predicting neutron star radii that are much different by over several kilometers. Now, how do I get the equation of state? This story goes back to the earliest part goes back to 1935 to Bethe-Weizsäcker mass formula, for which the idea was very simple, that the nuclear forces saturate and there must be an equilibrium density, and the nuclei surface, so they have added the surface terms, penalized by Coulomb repulsion, Coulomb term, and should be penalized by some isospin asymmetry between. There were some magic nuclei that didn't behave this quite much, so they call them shell corrections, and therefore the name magic nuclei comes. This model is very simple, yet it gives very good accurate description of finite nuclei for most cases. So Bethe-Weizsäcker formula constrains these parameters very well at around nuclear saturation density. What it doesn't tell is the dense dependence of these parameters. Essentially, it doesn't tell what would happen if the nuclear matter is taken off slightly. So that part is that I would like to talk about them. So this plot, you have a protons and neutrons are plotted, and isotopes are isotopic chart is plotted. Black spots you see stable isotopes. Extent of neutron-rich isotopes or proton-rich isotopes are primarily dictated by the equation of state of matter or proton-rich matter, and especially that we do not know very much. This one, we try to improve the Bethe-Weizsäcker mass formula by using nuclear energy density functionals. There are many nuclear energy density functionals. In this particular one, we use the so-called relativistic mean field model that are based on Lagrangian interactions between nucleons that exchange through various mesons. There are that you can introduce. In particular, you need a scalar meson and a vector meson for attraction and repulsion. And there are also two types of scalar mesons or vector mesons, isoscalar and isovector mesons. So we have got a scalar, isoscalar, vector isoscalar, and a vector isovector mesons that very much describe the properties of fine nuclei very well. In particular, the parameters are solely constrained by the ground properties of finite nuclei. Zero parameter of the isovector term and by ground source properties of some heavy neutron-rich nuclei. Kappa and lambda terms were introduced by Bogutta-Bodmer to get the so-called nuclear incompressibility of the smaller value that will be consistent with isoscalar giant monopole resonance. The lambda V terms were introduced by to discuss radii of different radii and also the neutron radius of heavy nuclei. And the zeta parameter was introduced by Muller originally, discussed that the maximum mass of neutron stars can be controlled by these parameters. In fact, also getting the equation of state of that are high densities relating to heavy ion collision. Parameters are unless the observation is so. So, that I was talking. And formula you see there is a thermodynamic relation between us. Want to know how the pressure is depending on density itself and also on this so-called isospin asymmetry, which is the density difference between neutrons and protons. For neutron-rich matter, it's useful to expand such energy per nucleon in, around isospin symmetric nuclear matter, which you would say one part is isospin symmetric nuclear matter equation of state, and the other part is known as the so-called symmetry energy term. The symmetry energy term on its own sometimes usefully expanded around the nuclear saturation, where the so-called J parameter is known as symmetry energy at saturation, and the L parameter is known as density slope. I will be talking about this density slope a lot because particularly in this plot, you will see energy per nucleon and symmetry energy is plotted as a function of density. For symmetric rates at saturation density, that's what of it. The slope is obviously zero, but the slope of the pure neutron matter, which is basically the difference, or the pure of it, is the addition to the symmetry energy. Is the slope of pure neutron matter, they're almost identical to the slope of the symmetry energy. And if I know the slope of this pure neutron matter or the slope of the symmetry energy, I would be knowing about the equation of state of neutron-rich matter. And narrowly of neutrons, that's why they're concentrating on. So I will skip these expansions, but I would like to talk that the symmetric nuclear matter equation of state very well constrained, especially its value at saturation is known to about 5% level. But when it comes to its density dependence, which is this K term, that's also very well known, especially recently by many experimental results concerning the value of nuclear incompressibility at about 10% level. So you may say the equation of state of symmetric nuclear matter is more or less known, at least to some densities. So this is a scalar grand molecular resonance, one of the general. Here, of matter as function of density, you can see various changes in the compressibility. For example, doesn't result much in a difference at high densities for the equation of state. Now, the very high density component of the equation of state can be constrained by the experimental data of heavy ion collisions or by observational data, such as the maximum mass of a neutron star. Those would very more or less constrain the equation of state of symmetric nuclear matter. This pressure versus density by this data is taken by flow analysis of collisions, where you smash two nuclei, and at the very high densities, you get a relationship between the pressure and density. This blue dot is, for example, is the constraint from maximum observed mass. So the equation of state is more or less constrained on this side. Therefore, the equation of state of matter is more or less known. Now, how do I get the equation of state of pure neutron matter, or let's say the symmetry energy, which is the difference of the two? The symmetry energy, again, as we decompose them in terms, and then just the symmetry energy itself, the experimental constraints are not. For example, these are all analysis of terrestrial experiments that were compiled by Professor Lee. And these are some astrophysical constraints that are actually very large. And when you go to actually high density component of this, it becomes even more uncertain. In particular, the slope of the symmetry energy, the experimental constraint is very unconstrained, you may say. Some experiments tell that it's than the others. So overall, it's main part. The K-sim is actually plotted. So if I plotted the equation of state of pure neutron, on the other hand, I get this. So some models predicting very stiff slopes, some of them very soft. Therefore, you get a range of models that very well describe the properties of nuclei, but then fail or give range of neutron star radii that are quite different. But what we know is there is one experimental property, so-called neutron of a nucleus, density slope. To understand what neutron skin is, imagine heavy nuclei of lead, for example, of 8. There are 82 protons and 126 neutrons. There are 44 extra neutrons that are there. The question is that where do you place them? Turns out if the pressure of matter is very strong, out of nuclei, and they form a layer of a neutron skin at the very upper form. And the larger the pressure is, of course, larger is the neutron skin thickness. And it turns out this neutron skin thickness is very strongly correlated with the dense slope of the symmetry energy, which in turn is actually related to the pressure of neutron matter at that density. Pressure of pure neutron matter pushes against the surface tension. Pressure. Same pressure. Therefore, neutron star radius of pressure or depending on the pressure value. The larger is the neutron skin, the larger is the you should see a bunch of correlation between the neutron skin thickness and several properties of ion nuclei and astrophysical properties of neutron. Go a little more about neutron skins. So here, I plot both proton distribution, density distribution, and neutron density distribution for LEAD 208 using one particular relativistic mean field model. The proton density distribution is very well known, and they were known in the 1950s. But the neutron density distribution is not very well known, mainly because all the probes that we have, electronic probes, they see electric charge and charged particles such as protons, and they are insensitive to neutrons because neutrons are neutral. And to actually see the neutron distribution, you would have to do some sort of the weak probes that I'll discuss soon. So there was an experiment, P-Rex, that has measured a neutron spin thickness by 0.33 Fermi and with very large error bars. How does this experiment work? As you shoot polarized electron beams into a heavy neutron-rich nuclei, the usual probe is the photons that sees all the proton distribution, and that's how we know are very well known. That's because the proton charge, electron charge is 1, charge is 0. But however, and when you do the d boson, when you probe a d boson exchange, then you're seeing the weak probes, and the weak proton charge is about 0.070, whereas the neutron weak charge is almost 1. It's negative 1. Very well. Were not known until now, and we are there are some now improvements. Factors is just yes. And as such, the polarized electron beams are shooted side, and the right side and measured, and parity-violating asymmetry is computed. As we know, the weak interaction violates parity. Therefore, you can measure this asymmetry parameter, which is dependent on this Weinberg factors. Essentially, measuring the parity-violating asymmetry tells you about. Now, there are experiments that are going to run this year in 2019 that primarily aim to measure this media to a very high accuracy. There are some other experiments that are planned at mines to measure the same things with higher accuracy. But so now getting to neutron star astrophysics. In particular, I will concentrate on these gravitational waves from binary neutron stars. About 1.5 years ago, neutron stars got merged, and everybody got excited because the first gravitational waves were detected from a binary neutron stars. For this, several gravitational waves were detected from black holes, and they were already exciting enough. But this was in particular a special event, mainly because not only that you could see gravitational waves, but you could point all your telescopes. And that's what was done immediately after. And many theories have been proven that were known for a long time, but there were no direct proof. And I will concentrate on something particular known as the so-called tidal deformability, for which when you have two neutron stars in a binary, when they are close by, the gravitational field is enough to tidally polarize the other neutron star in the same way that tidally polarize the these types. So this external gravitational field of one neutron star will quadruple deformation on the other one, and the coefficient of this relationship is known as the tidal polarizability, which reduces to the power fifth. And there is some other coefficient known as the tidal love number that is also structure of neutron stars. Now, how do I r to the power fifth, we can think of in terms of the regular electric dipole polarizability. For example, the electric dipole polarizability, and here is electric field. is related to dipole moment to coefficient known as electric dipole polarizability that is scaled as reduced to the power cube because of this matrix elements and the Coulomb forces being 1 over r. That gives you the correlation. For gravitational counterpart, because gravitational dipole moment vanishes. However, you quadrupole polarizability, you have gravitational field inducing quadrupole deformation. Coefficient is adaptive, as you said, and there is the matrix elements. Quadrupole moment are fourth, and gravitational 1 over r, so you get r to the power 3. So this contributes to gravitational wave emission, and it's very interesting. It has been known for a long time by some French authors, Paul and Amour, later by many others. They've been discussing this until there is a bunch of formulas that I don't want you to pay attention very much, but I would like to only say that the equation of state that matters in calculating this, and therefore, once you calculate it, you will get. Once you know the equation of state, you will exactly know what your tidal. How is it related to the neutron star radii? As we said, it's r to the power 5th. We already said that the radii of neutron star depends on whether the nuclear equation of state is stiff or soft. The smaller is the neutron star radii, and the stiffer the equation of state is, the larger is the neutron star radii. Therefore, the same should be expected for tidal polarizability, as you can see on in these pictures. Now, as two neutron stars try to merge, towards the merger, we can think in terms of Newtonian physics. As they start coming closer, you get induced quadrupole deformation that gets added onto the gravitational potential, which in turn advances the orbit of the phase changes. So when you see the gravitational wave phase towards the merger, there is an advance in this orbit. And that's how you can actually extract the gravitational quadrupole moment, this tidal deformability. For example, this cannot be seen in the case of black holes. For example, when you have a two black hole merger, you can see of the same mass. This is the waveform, and as I go to neutron star, there is an advance in the phase. So the orbit changes, and you see the advance in rotational phase. Due to that advance in rotational phase, you can actually extract, depending on how far away is, of course, the neutron star merger is, because the signal to noise ratio has to be very small. But if they are closer, then you can get actually very accurate results. We are very lucky because these two particular neutron stars were very close compared to what we expected, but I mean relatively very close. So the tidal deformability was actually measured. The largest stars obviously collide much earlier, therefore merge at a lower frequency, but the compact stars continue to orbit a little further. So you can see whether they are compact or not by simply also looking at their the waveform and at the collision. Also, you see at the size of the waveform, so you can see how fast it got advanced. So this was by LIGO-Lab, and it's arms detector, and they are very lucky that Indian LIGO is now going to get similar results, and also in the future we will have more detectors, and that will give us opportunity to locate to give a location of the neutron stars or black hole mergers very accurately. So gravitational wave chirp spectrogram is shown in here, for which it after a very few frequency evolution, a very few number of evolution, you immediately can get this value very accurately. In fact, this gravitational chirp mass was obtained to very high accuracy. That will tell you the ratio of the two masses. And in particular, they found in the original finding that the tidal deformability of one of these neutron stars, assuming it's a 1.4 solar mass, is less than 800. And In this plot, this is the original plot. They have the probability distribution for the two neutron stars tidal deformability or tidal polarizability, showing the 90% interval. The high stiff equation of are already ruled out. Now, if you did the same analysis with relativistic mean field models of a particular model, shows that is very highly accurately calibrated to all properties of finite. Find that such a 800 field would test that all models that predict larger values of this neutron skin of lead of part 0.28 must be ruled out. This part also particularly suggests that the neutron star radii should be about 10 kilometers. Or it tells that this density energy be more or less than about 110 MeV. But again, this is a particular model, and we to RMF models that are all accurately calibrated for different reasons. High the equation of state of symmetric nuclear matter is quite different. Some of them are already, for example, this one by heavy ion collision data. Nevertheless, we kept them just to what would be suggestions. And the others are also maybe ruled out because of the maximum mass of a neutron stars that have been recently suggested. Neutron star cannot be large. So then, by plotting that, we get mass radius correlation, as you can see, of this sort with different radii. And for example, for 1.5 solar mass, you get about from 12 kilometers all the way to about to 15 kilometers. But then gravitational waves just said all these models must be ruled out, and you've got something that's the same thing. And these are in the same of the paper. You can plot the two tidal deformabilities dictated by these models, and you can rule out all the stiff models, equation of state. And again, it suggests that the symmetry energy has to be about less than 100 MeV. In particular, the neutron skin thickness of lead should be about less than 0.028 Fermi. So a similar plot again with the neutron star radius and neutron skin on top, and you can see that the neutron star radii must be smaller than about 13.76 kilometers. So there is a very good correlation, as you can see, and this particular one suggests that, of course, smaller than this value. We didn't have a model for that, but we know that this is approximately about 80 MeV, or maybe about larger than that, but not too extremely large. So recently, we did a very thorough analysis in the sense that many analyses have been done on the equation of state, and combining all of them together, we took all about 100 skirmy interactions, put them all together, and either the formula star radius. You see this correlation is actually universal in the sense that they scale like r to the power fifth. And because skirmies are, these skirmy interactions are extremely different in dense dependence of symmetry energy and also symmetric nuclear matter equation of state, you do not get a very nice correlation with the density slope of the symmetry energy. However, we should admit that out of all these skirmies, only 5 of these were recently passed through all the tests that we know. In fact, as I was saying, the 10 models that are very highly accurately calibrated to properties of finite nuclei, you may say about the same about these 5 models. And these 5 models are shown in star color here. You can see them, and they suggest that the density slope of the symmetry energy must be. Now, tidal polarizability constrains the neutron skin to about 0.25 per mean. You may ask a question, what would an experimental result such as neutron skin measurement of 0.15 per mean, which is already told by the original QX experiment, imply on the value of tidal polarizability? Let's say, what's the minimum tidal polarizability that you can expect? a simple calculation shows that, for example, using those models, that the tidal deformability on the lower side has to be about 490. There are some larger. Yes, please. Okay, I think I'm hearing my. Okay, so there were some more recent developments on this. In particular, they found that they reanalyzed data and they found that tidal deformability is actually smaller than the one that they originally said. It's about 190 plus 390 minus 120. This such a very small tidal deformability is at the edge of current nuclear models that are, as you know, for example, for relativistic meaningful models. Some other models will actually describe it, but still it's a very it rules out many of the models that we know. And you may ask a question that what if actually the PREX one that measures 0.33 Fermi and the PREX-T2, for example, goes ahead and confirms such a very large central value of the neutron skin. In such a case, to understand that while the PREX collaboration or the measurements of neutron skin constrain the equation of state at about saturation density, and the central density of neutron stars are several times larger than that, which means the correlation with higher densities should be taken into account. In fact, the equation of state at higher density might be different. In particular, this may indicate that they should be, or maybe a phase transition at higher densities to some exotic phases of matter that are speculated up to now, but this would be some indirect proof, such as, for example, a transition to a quark core. Also, we recently showed that you can take the exact same density dependence of the symmetry energy around saturation density and then have the density dependence vary at high densities. For example, these two models are almost identical at about saturation density, but as they go to higher densities, they deviate. You can see there's a very high deviation in the value of the predicted tidal deformability as well. Therefore, a smaller tidal deformability would, for example, suggest that the equation of state, the nuclear symmetry energy at higher densities are very soft. Such an experiment is actually possible experimentally. For example, we recently showed that tidal deformability, as we said, is strongly correlated with the pressure of neutron matter at about twice nuclear saturation density. A very strong correlation. And while tidal deformability will constrain, had actually already constrained the pressure of neutron-rich matter at high densities, it's the experiment that's going to distinguish between the symmetric nuclear matter versus the symmetric energy. Here is this is original experiment, and the symmetry energy is shown as the soft on the bottom function of pressure. Now, so here, this experiment is old, but the new updated experiment is being proposed, and in the heavy ion collision and they are aiming to get better results on the pressure of matter at high density. So there are lots of interesting connections that you can make. Our understanding of equation of state of dense matter, connected it to the particular thickness, and also infer some constraint on the density dependence of the symmetry energy, and also provided some lower limit due to the lower value of the neutron skin. And we went on to speculate that TRX2 and CRX measurements would be very essential to give us useful information on the equation of state at and below saturation, whereas heavy ion collisions experiment would constrain it at sub-saturation densities. In combination with future binary neutron star mergers and neutron star radii observations from NICER, this should provide even further tighter constraints on the role in the determination of the state, but not very much on the tidal deformability. There are more exciting opportunities that are ahead, and there's a very strong synergies being developed among nuclear physics, astrophysics, gravitational wave astronomy, on all these other physics, particle physics, and X-ray physics that should yet uncover that we know about neutron stars. And I would like to thank you all for talk and thank my collaborators who have contributed to this research. Thank you so much, and I'll take questions.
Yeah.
Thank you very much, Farrukh.
Thank you.
Hello.
Yeah.
Thank you. Yeah.
No.
I mean, anybody has any questions? Hello.
Yeah. Subrat. Tell me the question.
It's muted, maybe.
Yeah.
You can put a video.
I think
I
you
have a
have to on the. Okay, then Abdul, you can ask first.
Yes, I have one question. How do you get the neutron star density distribution as a function of R?
So it's a theoretical calculation. So I just solve hydrostatic structure equations using a given model. So that there were two equation of state models that you put into this pressure gradient and equations and basically solve the hydrostatic structure equations using two conditions: charge neutrality and chemical equilibrium conditions. And the density distribution comes out this as a theoretical prediction.
Okay.
Okay, Subrat.
So my question is that so in a quadrupole moment like electric field and charge distributions, so basically the quadrupole moment gives the charge distributions. Uh,
For electric one.
Yes, yes.
Yes. So means that if the quadrupole moment is zero, I think so the charge should be spherically symmetric distributed.
That's
So,
correct.
so similar types of things here. Can you say that the distribution of matter gives the tidal deformability in the neutron star?
Exactly.
Yes, so exactly. It's a distribution of matter. In fact, if you have a spherical neutron star without a quadrupole deformation, then you don't get any gravitational waveform.
So that's actually indicate that the neutron star are not purely spherical objects.
Yeah, because it will be getting this tidally deformed. As you get tidally deformed, then you get an additional quadrupole deformation. So redistribution of masses. And this redistribution of masses will generate gravitational waves. And that's what you are measuring. Yeah.
But the problem, how the tidal deformability give the information about the component of that matter?
So the tidal deformability on its own does not tell you what's the properties or is the measure of quadrupole deformation, how deformed it is or how well it's squeezed. So that it will tell only how stiff is the neutron star matter. For example, if you have got a very soft neutron star matter, then it's compact and it's very difficult to polarize. But if you've got a very large neutron star, then it's very easy to polarize and you get a larger quadrupole deformation. So
means they are more highly deformed. They can deformed. If they are soft, they can deform.
It's easy to deform large stars.
Easy to do. But it cannot directly say anything about the component of matter.
Exactly. That's the whole point. Because it cannot tell anything about the component of the matter, you have to probe it with some models, theoretical models. And nuclear physics tells you exactly what would be the ones that's causing this to do so. So one of particular thing that we said is the neutron skin, for example, measurement would probably tell us the equation of state at about saturation density. So it would tell some information at about saturation density, but it would leave out anything at higher densities. So if there is any inconsistency between the two, then you would go ahead and speculate onto saying that maybe there is some additional physics involved, like such as exotic phases. Even if that's inconsistent, or let's say something wrong happens, then you actually have to do that experiment, which is done by heavy ion collisions. So the experiments will tell you what's happening, but tidal deformability cannot tell you. It just tells.
It can only give that its equation of state steep or soft.
Yes, so it just tells you the global picture of it. Like it just gives you basically the mass and radius, you would say.
So second thing is that when we correlate among the tidal deformability of one canonical mass and radius, tidal deformability of 1.4 solar mass and corresponding density. We correlate for suppose we find a correlation between the tidal deformability and the radius of that canonical mass.
So
you have shown the fact picture that
let me see. So, do you see my picture? Do you see my slides, right?
Yes. You have shown.
Okay, let me go a little quicker. So
in the last part of that. Okay. Here. Here the pressure. That's the 53 slide number.
53. This one.
Okay. This one also. Here we have shown. You have shown that the correlation between the pressure and the tidal deformability. No. This is the symmetry energy, L slope, and this is the. Similarly, other people. This one. They have shown the pressure at 2 times of the saturation density and the tidal deformability. Hello?
Maybe I didn't understand you. So yes, there is a strong correlation between the tidal deformability and pressure at twice saturation density.
So why this 2 times saturation density?
Yes, exactly. So the neutron stars, if you think of them as an average density, because the density in neutron stars spans several orders of magnitude, the so-called average density of neutron stars happens to be about 2 saturation density. It depends, of course, on the mass of the neutron star. If you have a very massive neutron star, maybe the average density is about 3 saturation density. But if you have got smaller stars and it's lower, because this is a cumulative process in the same way as the mass content, because it's a mass distribution of the things that we have to measure. So it turns out that it would be most sensitive to this average density of about 2 saturation density.
So we can we say that like similar type of things, because we are measuring the neutron star which have average density around 2 times of the pressure, 2 times of the saturation density. So that's why their properties, whatever we are measuring, that is correlated with the pressure.
Yes, with the pressure at about twice saturation density, or maybe at the average density of a neutron star. We have actually shown that using some correlation analysis, you can show that properties of neutron stars in general, like such as radii, for example, are very strongly correlated with the so-called average density of a neutron star.
Also the T-Sang, this T-Sang, CY T-Sang, they have she have also already shown one of her paper that if you go to the higher density, the correlation became more strong and stronger.
Pressure, right? Do I understand correctly?
Not pressure, not for the L symmetry value.
Yes. So for the symmetry energy, right?
Symmetry energy and the slope of the symmetry energy, there is no correlation here.
Yes. So with the slope of the symmetry energy, the correlation is usually weak at saturation density. But again, the same idea. If you go higher and higher, it becomes more correlated. That's correct. That's the whole current experimental values constrain the value of the symmetry energy at about saturation density. If you do so, then the tidal deformability and the symmetry energy are not quite correlated. Maybe correlated with the slope, but not with the symmetry energy itself. But if you go higher, then they are. So the point here was that the heavy ion collision experiments are also important because they would tell you something more.
Yes. So one question, another one questions. So this is the whatever the GW170817 is purely Newton star. So is there any evidence there is some hyperon is there?
So at the moment, as is, no, because there are models without hyperons that can very easily tell. I mean, predict the same tidal deformability
No,
as.
but
Oh,
but
you
these are all models.
mean observationally?
Observationally.
I do not know. I think probably I haven't followed everything in the papers, but as far as I know, that using nuclear matter models, they predicted what would be the number of certain elements that actually match the observations for the.
No. My question is that can we study that hyperon puzzle using this tidal deformability information?
May you repeat, please? Because I may use. Do you mean that with using models with hyperons, can we get the same deformability?
Deformability.
So I haven't done personally, but as far as I know, with hyperons, usually it's very difficult to get to the two solar mass. There are some models that involves hyperons and includes the three body nuclear forces that gives the two solar mass. From what I know of their radii, I believe they should be consistent because the radii that they predict is smaller than what is the tidal deformity is currently given. So I'm thinking that it's still consistent.
No, but the problem is that the hyperon coupling constant that plays a very significant role in calculating this radius and maximum mass, all these things. So if you choose proper hyperon coupling constant, we can fix that things, that radius and mass things.
So yeah, this is the thing I'm saying. So with the proper coupling constant, even with proper coupling constants, there were a problem with the.
They have a problem. I know that's a big problem, that the proper coupling constant, value of the proper coupling constant.
Not solved, or maybe pushed at least a little further by taking into account the three body nuclear forces, and by collaborators. Yeah. So I'm guessing, but I do not know the calculations given on the mass n versus radius plots that they have. I believe it should be consistent with the current tidal deformability measurement. I mean, just one single measurement. So yeah, we should wait for the next ones too.
Okay. Bhuya,
Thanks.
Okay. Thanks, Fattoyev, for a nice talk. So my question is about that the tidal deformability. How effective it will be constrain the radius of twin star?
Two neutron star, right?
Yeah.
Two mass neutrons.
Yeah.
Twin star.
Twin star, yes. Twin star means
twin star.
we can constrain the radius of the twin star.
If they merge together.
Yes.
Post merger information is unfortunate, is very messy, and so the tidal deformability beforehand is measured, and at the time of merger, it gets the things get complex, and the way I understand much of the information post star, and in particular this particular measurement is assumed that they form a black hole, and if you have a black hole, then you don't have neutron star. Post a lot, and how do you get the radius of that one? Yeah.
Recently, I have seen one paper from the Germany, the German group from German. They are just measuring. They using various of equation of states from the SCORM and also relativistic model. They try to constrain the radius of the twin star. So, but they found that the constraint putting the tidal deformability as observable to constrain the twin star radius is not effective. Means they found a very big range, like a 6 to 14 or 18, like that. I am very precise number I don't have at present, but this like this. So that point, because it will be interesting if we have to constrain the radius of twin star using the tidal deformability data. That is just interesting. Have a question points. Okay, not each of questions, of course.
Thank you. Is that the red solar group or?
Hello.
Yeah, I was wondering. Solar group.
Farrukh, I have a question. Hello.
Yes, please.
Hello, Farrukh.
Yes, I can hear.
With the existing data. Hello, Farrukh. The question
Yes,
I want to ask is with the nuclei have at hand, can we say something about the value of neutron skin thickness?
I'm afraid I'm not hearing all of it. There is this disconnection.
So what I'm saying, with the existing data on the finite nuclei, can we say that what could be most likely?
I'm sorry. So maybe I will repeat approximately what I heard. With the existing finite nuclei data, can we say anything about tidal polarizability? Is that what was the question?
No. Value of neutron skin thickness. With the existing data, what we have at hand, can we say something about the likely value of neutron skin thickness?
Yes, with the current tidal polarizability, if only I use the so-called relativistic mean field models, which suggest that the neutron skin thickness is smaller than 0.25 per mean. It wouldn't tell, of course, the lower bound, but the upper bound is kind of fixed. So considering only relativistic mean field models that are accurately calibrated and taking into account a proper class equation of state, you get, let's say, the tidal deformability of about 800 would suggest it's below 0.28 per mean. But if you think now it's updated about 500 something, then it's actually much smaller, maybe smaller than 0.20 per mean. I haven't done calculations for that yet.
Yeah, that's what exactly I wanted to know, because it looks like that, I mean, the finite nuclear data we have, I mean, even there was a paper in 2012 in PRL by this Muller on the finite nuclei binding, the value of L turned out to be close to 70. So, look what data we have on a finite nuclei, that is telling us that the skin thickness could be likely towards the lower side.
Yes.
At the same time, of the
I believe if I heard correctly, we are talking about finite nuclei, and I believe the finite nuclei predictions are when they talk about the value of the slope of the symmetry energy. Personally, I do not have too much trust in their error bars. There are some good calculations, theoretical calculations of pure neutron matter that suggest the value of the slope of the symmetry energy should be small, about 50 MeV, and with plus minus 10 MeV. But still, if you look at their error bars, it's actually wide in the sense that it's not quite well constrained for the. So yeah, given that the slope of the symmetry energy is not actually well constrained, in my opinion, then I wouldn't say much about the neutron skin thickness. I think, yeah, unfortunately, I'm getting some sort of.
what you are saying, point.
So, is there any question? Tommy? Your voice is not audible.
I have a question.
Can you hear me?
Yeah.
Yeah.
Ask on Tommy.
Yeah. So actually, I do not have much idea about this tidal deformability and all this kind of things. I work in some different kind of aspects, but I know about the relativistic mean field model, and I use it in my calculations and interaction. And so I just want to know, while you were talking about neutron skin thickness, so you were talking about the whole as a whole neutron star thickness, or the individual neutron thickness? That is not, I don't get the much about idea. What is the neutron skin thickness here?
So what I was trying to communicate was that the neutron skin thickness is strongly correlated with the radius of neutron star.
Yes.
In a sense, I should have said the neutron radius is strongly correlated with the neutron star radius, but because the neutron radius is the difference between the neutron proton radius plus neutron skin,
Yes.
so
Yes.
very correlated with the neutron star radius. And neutron star radius measurements are very active. You have got NICER, you have got tidal deformability measurements, all of which would constrain neutron star radii. And neutron skin thickness is a hot topic in experimental
Yes.
point. That's how I was communicating. Yeah, trying to.
Okay. Yeah, I got it.
Abdul.
Yes.
Abdul, you can ask.
Yes, I am asking. You presented in one of your slides that this neutron skin thickness of layer 208 is constant from DW data that is found to be 0.25 for me. Okay, so I did not grasp this thing, how the neutron skin thickness of layer is constant. In what way it is constant from DW data?
Constraint, right? So
Yeah.
So maybe I should go to the slide to make some connection. Are basically model constraints. So if you look, for example, at the various highly accurately calibrated
I am not able to hear you.
I'm sorry. Can you hear me?
Yes. Go on.
So I was saying that if you plot various model predictions of tidal deformability versus neutron star radii, you can see, for example, there is a good correlation. Same goes with the neutron thickness, which of course we had another picture as well. For which, if you use the upper bound on the gravitational waves tidal deformability line, and every model above it is these models are excluded, which means all these models that have smaller than about 0.25.
Okay, I got it.
Essentially, the idea is that the softer equation states are the ones that are currently in the play, and they predict smaller neutron skin.
Okay, but the Prex observation are about 0.33 for me, right? So there is some type of experimental discrepancy between two experiments, right?
Farrukh?
Yes, please.
Yes, I mean the Prex data shows that this skin thickness of layer is around 0.33 for me. So
yes.
Yes, so I mean, how to resolve this problem of these
Yes,
experimental.
the original T-Rex experiment that was run in 2011, unfortunately, it came with this lots of systematic errors. They had some problems with the leaking of the. They've got this large systematic errors of about 0. Per me. So it's not 0.33, but 0.33 plus 0.16 minus. Essentially covers the whole range of the neutron. there is no inconsistency as of now. But
Okay.
again, as you say, in the future, if that happens to be actually the value, the very small error bars, an inconsistency, which can be resolved by simply taking the equation of state at higher densities to be soft, which means you can calculating that it could be either due to density dependence of the symmetry energy behavior into for example, hyperons at high density or maybe delta resonance and Farrukh. So you can